Hello everyone, I'm Tianxin Tang from Georgia Tech. I'm going to present a joint work with my advisor / our board driver on privacy-preserving approximate key-nearest neighbor search that hides access, query, and volume patterns. So let's get started by looking at the KN problem. Over some metric space, given a dataset, construct a data structure that returns a point which is the ith nearest neighbor of the query point for all I from 1 to k. In this illustration, suppose k equals to 2 and let the black point know the query point and all the red points are the points in the database. We say P1 is queues 1NN and P2 is queues 2NN. As we all know that KNN can be used as a basic machine learning classification tool and has numerous applications, include content-based image search, face recognition, medical diagnosis, and anomaly detection. However, the issue is that in our daily life, high-dimensional data such as pictures, videos are getting more prevalent, and finding the exact KNNs suffers an inefficiency problem. To deal with this, we resort to the approximated version, namely AKNN, which is appropriate for many applications that allow sacrificing some precision for efficiency. So now it's the time to define approximate KNN problem, or epsilon delta AKNN. It asks the following question: can we construct data structure that returns a point whose distance from the query is no more than 1 plus epsilon times the distance of the two ith nearest neighbor, with probability at least 1 minus delta? In this illustration, suppose k equals 2, P1 is queues 1NN, and distance between Q and P1 is R1. And P2 is queues 2NN, the distance between 2 points is R2. Now we say that P1 and P2 are queues approximately 1NN since both points reside in the orange circle centered at Q of radius 1 plus epsilon times R1. And P2 and P3 are queues approximately 2NN. We're now ready to define the problem setting. That is, we want to preserve privacy when performing AKNN on our private data. Especially, we're focusing on the outsource setting, where the client has the data and the secret key, since it is common nowadays to outsource our data to the client services offered by companies such as Apple and Google for easy access. Social encryption, or SE, is an area that explicitly targets the outsource setting, offers privacy-preserving solutions, accessing encrypted data. In this illustration, the client has a secret key and k equals to 2. She will first encrypt her files and tags and send to the server. During the search stage, she will send the query tag, and the server will find the tags to NN's associated files and send back to the client. There are a couple of SE schemes that support KNN queries. However, some of the schemes leak the relative distance, and some leaks common leakage patterns of SE, such as query pattern, sometimes volume pattern, and access pattern. I will briefly describe what those common SE leakage patterns are. First, the volume pattern. The adversary can glean information, for example, the number of matched encrypted files, by observing the transcript size. In this illustration, the orange query has 2 matched orange files, while the blue query only has 1 matched file. Next, the query pattern. It implies whether the queries are repeated. In this case, the orange queries have been made twice, and the blue query has been made once. Finally, the access pattern. It reveals what encrypted files that the client has accessed on the server. These are all common SE leakage patterns, and initially people were okay with such leakage, as allowing this provided fast SE solutions. But in recent years, emerging attacks exploiting those leakages have successfully recovered the query or reconstruct the dataset, and thus becomes a problem. There are secure SE solutions hiding common SE patterns, but with strong assumptions. For example, Oblix using STX hides the access and query pattern. Medway et al. Proposes a secure KNN scheme relying on non-colluding servers, hides the access pattern. However, we want to solve the problem without such strong assumptions. Can we have a practical secure approximate KNN protocol that hides access, query, and volume pattern in an outsourced environment? Because we are dealing with hiding the access pattern, and it's well known that oblivious RAM hides that. So can we use ORAM in a straightforward manner? The bad news is a video in 2015 showed that if some of the keywords match all the documents, then it leads to inefficiency. Namely, for a single keyword search, it costs more bandwidth than transferring the whole encrypted database. However, luckily for us, we observed that solving AKNN with ORAM-based constructions is more feasible than general keyword search, since the number of data points or documents associated with each query tag can be bounded. I will summarize the contributions for our work, which include defining security of privacy-preserving AKN protocol, PPAKNN, defining security of oblivious map with encryption, OMAP, a generic PPAKN protocol based on OMAP with security analysis. And finally, we evaluated our constructions through implementations and experiments. Before going into more details of the construction, let's move on to define the syntax, or in other words, the functionality of the scheme. A privacy-preserving AKNN protocol, or PPAKNN, is defined for metric space, for example, the Euclidean space, and message space, by two algorithms, setup, decryption, and the two interactive algorithms, search and update. I have made some illustrations for the setup, search, update algorithm, and omitted decryption as it is more straightforward. Given error factor epsilon, failure probability delta, parameter z, which may contain auxiliary information about the message distribution, the setup algorithm takes as input those parameters and a list of files and tags. These will then output the encrypted database, which will be outsourced to the server, a secret key kept by the client, a public parameter kmax that is the largest k supported by the system's AKNN search. For the search algorithm, the client will input her secret key, a secret parameter k that is from 1 to kmax, and her query tag. The server will input the encrypted database. At the end of the search algorithm, the client will receive the response, and the server will update the encrypted database. The update algorithm runs similarly, with the exception that the client instead inputs an operation type, either it's an add or remove. She also inputs a tag and associated file. At the end of the update algorithm, the client will receive no output. Since we have the syntax ready, now let's move to the correctness and efficiency requirements for PPAKNN constructions. We want epsilon delta correct for search, and perfect correctness for both update and decryption. As for the efficiency aspect, we want a big O of polylog n computational and big O of polylog n communication bandwidth, assuming kmax is much less than n, where n is the number of items in the dataset. Next, we will define the security. We provide a simulation-based security notion with leakage functions for setup, search, and update. In both experiments, the adversary is given the encrypted database. It can adaptively choose the queries, receive the function outputs, and the transcripts produced by the honest executions of the real protocol in the real world. In the ideal world, the simulator needs to produce the encrypted database and the transcripts based on the allowed leakage. Our definition requires that there exists a PPT simulator for every non-uniform PPT adversary A. A can only distinguish the real and ideal world with negligible probability. Next, the very crucial part, we need to define the security sufficient for practice. We model the server as an honest but curious adversary. Once the server is compromised, the encrypted database should be resistant to the snapshot attack. Namely, no efficient adversary is capable of learning the underlying plaintext by examining the encrypted database. If constructions satisfy our security definition, then it implies that all efficient adversaries cannot learn information other than the allowed leakage explicitly specified in the constructions. In our case, we aim at a construction basically with no leakage, whereas the secure definition is for general case, so it has an abstract leakage profile. Before going into details of building a PPAKN construction, let's start with studying how to solve the unsecured AKN first. First, we need to introduce the approximate near neighbor problem, or CRNN. And it asks the following question. Given a closeness threshold R, approximation factor C, can we construct data structure so that for any QRQ with probability at least 1 minus delta, if there are points within Q's R radius, the returns point in the dataset so that it is at most C times R far away from Q? And outputs yes. Otherwise, outputs no. In this illustration, suppose C equals 1.2 and the distance between Q and P1 is R. Then we say P1 and P2 are Q's CRNN, since both points are within the orange circle centered at Q of radius C times R. So how to solve the CRNN problem? We use an algorithm called ELSH CRNN, which is built on locality sensitive hashing in extension form, or ELSH we called in our work. Essentially, ELSH is a vector of random hash functions. The closer the data, the higher probability they will share the same hashes or ELSH tags. So the ELSH CRNN algorithm uses a lookup map that stores the ELSH tags of all the data points in the keyword field. It finds the RNN by examining points sharing overlapped ELSH tags with a keyword point. Now we are ready to solve the unsecured AKNN problem. We found in literature that we can solve AKNN by reducing it to a sequence of CRNN subproblems, for example of size S in this illustration. We can then solve each subproblem with ELSH CRNN. This is a known idea, but with no correctness proof, so we provide one in our work. So far, all I have described are for unsecured AKNN solution. So how to build a secure one? The idea is that we can instantiate the unsecured lookup map with a secured version. The building block we call oblivious map with encryption, or OMAP-E. Note that the existing secure definition for oblivious map is not sufficient, as it only provides obliviousness, namely hiding the access pattern. But it does not provide data privacy in the presence of adaptive adversaries. Therefore, we propose a secure definition for OMAP-E addressing those security properties. We briefly discussed the syntax for OMAP-E, which is used in later discussion. So OMAP-E is defined for message space by 3 algorithms: key generation, setup, decryption, and one interactive algorithm access that supports standard map operations, including keyword lookup, add, and remove. We show that we can build OMAP-E using oblivious map together with ECPA's metric encryption scheme. There are 2 oblivious map candidates. One is oblivious AVO tree, and the other is oblivious B skiplets. Both can be built using non-recursive position-based ORAM, encrypting each blocks of the underlying ORAM and re-encrypting when writing back the blocks will satisfy our new security definition for OMAP-E. The security of OMAP-E construction is stronger than structured encryption since it hides the type of the update operations. As for the leakage part, during the accessing stage for map operations, the leakage is empty. The setup leakage only contains public parameters of the oblivious map. we can conclude that OMAP constructions hide axis, query, and volume pattern. Finally, we are ready to build our PPA-KN construction. Let's take a look at the setup stage. The client will first run the OMAP key generation and get her secret key. She will then run the compute parameters algorithm. The algorithm will output EL search parameters and key max. EL search parameters will then be used to extract the EL tags, and the tags are used to construct a map with her local files. Finally, the client will run the OMAP setup stage, and it will take as input her secret key, and the lookup map outputs them into a database that is stored on the server. The search and update algorithm of PPA-KN construction are built using similar idea. For search, it will run the OMAP access as a sub-protocol a fixed number of times to accomplish the AKN search. For update, it also runs the OMAP access a fixed number of times to update the underlying OMAP. Since we have the construction ready, we can now move to analyze the correctness and efficiency. The correctness part is not straightforward. We provide a proof on correctness and an upper bound on the size of returned results for efficiency. And you can find more details of our constructions regarding the efficiency aspect in our paper. We prove the security of our PPA-KN constructions relying on NCPA of the underlying standard symmetric encryption scheme and adaptive obliviousness of the underlying oblivious map. The leakage profile contains the setup leakage, which are the public parameters of OMAP.setup. Both search and update leaks the corresponding number of executions of OMAP access. Due to time limit, I will briefly go through the implementation part. We completed our PPA-KN protocol incorporating the ELSH library together with two new implementations of OMAP. We tested and selected the ELSH parameters on benchmark datasets tailored for AKN search. In addition, we proposed two optimization methods, one through batch queries and the other through parallel access. We found through our experiments that OB-skipless-based construction performed much better than the OA-view tree-based ones. And finally, for a much larger database or smaller keymax, the offset compared with the baseline increases, since the overall bandwidth cost is below of the keymax times log n squared. So this concludes my talk. Thank you for listening, and if you have any question, we can meet at the following poster session.